The simulator models the physical phenomenon of mode-I tensile fracture mechanics and elastic plastic stress field evolution using an advanced confocal elliptic hyperbolic coordinate system. It visually demonstrates how a structural material behaves under tension at a sharp crack tip, where theoretical calculations create intense stress concentrations that scale inversely with the square root of the local radius vector. In real-world engineering materials, these mathematical infinity spikes are naturally diffused by localized plastic deformation zones, modeled via Irwin's yield criterion, which create a distinct multi-lobed dog bone or butterfly envelope where the metal permanently yields and stretches to absorb the mechanical energy. When the localized stress intensity factor breaches the material's built-in fracture resistance threshold, an unstable structural failure state is triggered, forcing a real-time propagation loop where the defect dynamically tears along continuous hyperbolic coordinate trajectories while the surrounding plastic energy dissipation zone balloons outward to manage the increasing structural burden.